So, hello everyone, welcome back to the YouTube channel Devotion of Knowledge. We are back again with a very another interesting video. It is about graph data structure. Our previous video was also regarding Dijkstra's algorithm. Today we are also going to understand another algorithm on the graph, which is cycle detection. Now, graphs are of mainly two types. One is directed, another is undirected. So we are going to understand about undirected graph. And as you would be aware, whenever graph comes into the picture, there are mainly two approaches to solve or understand any algorithm. They are, one is depth first search, another is breadth first search. Today we are going to understand depth first search and in undirected graph. Please make sure. So let us head straight to the graph. Yes, this is our graph data structure, on which we are going to understand how to write the code, how the algorithm works to detect that whether a cycle is present or not in the graph. So this is the graph we are given, and it is adjacency list and it is visited array, as visited array is a must in every graph problem. So let us start. Now let us understand some terminologies. This node 2, it can be derived, means it can be reached from this node 1, node 3 and node 6. For example, there is some node A, and from node A, by applying any traversal technique, we are reaching this node B from this. So in this case, A is parent of B. Please make sure this is a very important terminology that we will be requiring in cycle detections understanding. If we are reaching any node B from any particular node, let us name it as A, then B is a child of A and A is a parent of B. Okay? Okay. Now let's move directly to the main understanding of the algorithm. Okay. Wait a second. Okay, done. We are back. Here we are given a graph. As you can see, first node is 1. So as we are going to use DFS, first of all, we will code DFS for 1. Okay. And as this is adjacency list, so all the elements of present in the adjacency list of 1 will be called. We will mark this as visited 1. DFS of 1 will call DFS for 2. Now, okay, wait a second. 1 will be also present in the list. Okay, adjacency list of 2. Now, when DFS of 2 is called, there are 3 elements in the adjacency list of 2. One is 3, 6, and another one is 1. Now, when we call DFS for 1, you will see that, oh, 1 is already visited and 1 is the parent of 2. As you understood right now, we are reaching 2 from 1. So 1 is considered as a parent, 1 is considered as a parent of 2. Okay. So 1 is already visited. See, these are for 1, 2, 3, 4, 5, and 6 nodes. Okay. We are seeing that, oh my god, 1 is already visited. There can be some error, but no, 1 is the parent of 2. And it is acceptable. Okay. Then another element in this adjacency list of 2 is 3. So we will call DFS for 3. Okay. See, 1 and 2 are already been visited and 3 will be also visited, as we are calling DFS for 3. Okay. On 3, it will call DFS for 2. But oh my god, 2 is already visited. No worries. 2 is a present of 3. So there is not any concern, or there is not any thing which we should take care of. Okay, done. Now it will call DFS of 4, as 4 is in the list of 3, DFS of 4. Okay, 4 will call for 3 first. We will mark 4 as visited. Now 4 will call for DFS call for 3, but 3 is already visited. No worries, 3 is a parent of 4. Okay, so 4 will call DFS for 5. Okay, DFS for 5. Okay, now we will iterate in the adjacency list of 5. Initial 4 will come, but 4 is already visited, and 4 is also a parent of 5. No worries. We will call the remaining element in the adjacency list of 5, which is 6. Now we have make the call for 6 also. This is our visited array. Now the twist will come. We have started from the node number 1. We make a respective DFS recursive calls for each and every node as per the adjacency list of the graph. So as per this trend, now we have made 6 depth first search calls. So we were standing here, then we came to here, 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 and here. Currently we are standing on the node number 6. We started from here and we are standing particularly at this juncture. Okay. Now in the adjacency list of 6, the one element is 5, another element is 2. Okay. First of all, it will call a DFS for 5, but it won't be executed because 5 is already visited, as well as 5 is the parent of 6. Okay. But the next thing will happen that 6 will call DFS for 2. 6 will call DFS for 2. Okay. But 2 is already visited. Please make sure. Please pay attention. 5 is done. 5 is parent of 6. No worries. Now it will call DFS call for 2. Okay. No worries. DFS call for 2. But 2 is already visited as it is 1 year, and 2 is also not a parent of 6. Let me repeat again. 2 is already visited and it is not a parent of 6. What does this mean? What does this mean? That we are uh, going to a node which is already visited and it is not even a parent of 6, which means we were on this path and we are going to that particular node which is already visited, which is not also a parent of 6, which means it is a presence of cycle. It is presence of cycle. Then only it is possible, because we are going to the particular node which is already visited into the visited array, and it is also not even a parent of the particular node at which we are standing right now. It only means that there is a cycle in the graph. I hope this thing is clear to you. Simply we are doing just DFS calls for all the adjacent elements present in the list, and we are making sure that if they are visited, that particular node should be the parent of the present node. Okay, up to node number 6, it was going smooth, but as soon as DFS call for 2 was made, the condition was checked that 2 is visited and 2 is not a parent of 6, which means presence of cycle. Simple. We went from this. Now on going to this node, it is already visited and it is not even a parent of 6 because we went from this side. So 5 is the parent of 6. I hope this explanation is clear to you. Simple. Algorithm is completed. Understanding is completed. Now we will straightly head to the code and see, yes, that there is some possibility also. Okay, we will see in the code where we are going to write. I will be attaching the link of this practice section as well in the comment section, so that you people can practice this question here. Adjacency list we are given, and see, connected components can also be present in the graph, but No worries. We will take care of them also. We will see how. Expected time complexity should be O of V plus E and space complexity should be O of V. We are also going to understand the time complexity at the end of the video. So please make sure you remain in the video till the end of the video. So let us start writing the code. First of all, we have to make vector of int of visited. It will be of the size of V and initially the all will be marked as 0. Okay, and this is the graph given to us. Let us make sure that the recording is still going on. Yes, recording is still going on. Now, we will be going through each and every node from 0 to V. 0 to V minus 1. Okay. Now, if that node is not visited, then we will be boolean b equal to, we will be calling a DFS call for this particular node. We will be passing visited adjacency list node parent of the node, which will be minus 1. We will understand why we are passing minus 1, and the present node I. Okay. Let us write the code for DFS. We are getting a visited array. We will be getting adjacency list, which is vector of vector. Int parent node. Okay. Now we will mark that particular node equal to 1. Okay. That particular node is marked as equal to 1. Now we will be calling DFS calls for each and every element present in the adjacency list of the particular node that we are currently standing right now. Okay. So for auto IT, it will be child of that particular nodes that we are standing. So auto IT child, it will be in the adjacency list of node. Okay. Bool B equal to DFS call for same. We will be passing visited array adjacency list. Parent will be node here and child. Simple. And if it returns true, if B equal to true, return true. Okay. When we will be calling this DFS call, please make sure only when if visited of child is 0, then only we will be calling this particular call for DFS. Okay. If it is not visited, this is the one case. Else, in else there are only two options. If it is visited, then the particular node that is visited, it should be a parent of the particular node. So if that node at which we are going right now, if child is not equal to parent, means if it is not equal to parent, then we will return true. And if none of the conditions hold true, we will return false. Okay, I hope it is clear to you. and if this boolean b that we have called dfs, it will return boolean. If b equal to true, if b equal to true, return true. Return false. Simple. I hope this code is clear to you. Let us run this program and see if there are any error or not. Child is not equal to parent. Okay, if condition, if child is not equal to parent. Okay, okay, the code is running. Let's submit it and see what's the result we are getting. Okay, all the test cases are passed successfully, and let us understand why I have passed -1. See, uh, we will start from the first node itself as it is 1. So for the starting node, there won't be any kind of cycle present. Let me repeat. For the starting node, there won't be any kind of cycle present. So we will be just calling all the respective calls for the adjacent elements present in the list of that starting node. So as I have included the parent in the function, so I have to pass any dummy value for the starting node. That's why we have passed -1. And it will be also useful when we suppose it's 6, 7, 8, 9. Suppose graph is like this. So there are, as you can see, there are three different components. One is this one, one is this one is this one. So after completing up to here, it will go here, means it will start calling from here, when as it is starting node. So we have to pass something as a dummy in the function, so we will just pass -1. I hope this thing is clear to you guys. Okay, now let us talk about time complexity. Let us talk about time complexity. It will be capital of V plus E. Let us understand how. Let us consider, as it is a worst case, we have to consider the densest graph possible. It means every node is connected to each and every node. Suppose let us consider like this. So it is the densest graph possible. Yes or no? Okay. And here we are running the loop for 0 to V, means 0 to V minus 1 means for all the vertices. So the loop will run for V times for sure, because we are running for the loop. We have to check that whether there is element which is not visited. For example, in different components can be also present. So we will be running a loop for the V times. Then as loop is running for the V times, and for example, this is the densest graph possible, 1. So 1 will be having 2 in the list, 1 will be having 3 in the list, 1 will be also having 4 in the list. Yes or no? Okay. So for each and every node, here 3, 6, 1. Now as it is an undirected graph, so one edge is equal to twice. I hope it is clear, because in one edge you can go on this side also and you can go on this side also. Okay. So for, if the densest graph is there on one, in the worst case, if one is connected to each and every element, then that particular call will be for e times, its number of edges. V equal to vertices, E equal to edges. I hope it is clear to you, because see, recursion is there. So in recursion, we have to see that how much times that first recursive call is being there. So it will be of V, and that particular call can call how much times to the different one. So it will be of V plus E, and space complexity will be of V, because we are using visited array as well to make sure that each and every element is visited or not. So that's why the complexity will be of V plus E. I hope this concept is clear to you, and it was for undirected graph. For directed graph, we have to maintain one vector which includes the nodes which were present in the current graph, because if path is like this, so in one path this node will be visited. Let us make sure all of them are visited, and now we are on this path. So this node is already visited, we are on this path, but this node is visited, but this node is not present on this path right now. So it is visited, but it is not present on the path right now. So it won't be cycle present there. So I hope this video is clear to you guys. If you are finding anything interesting or new in the video, please make sure you follow the channel for more related content and for the more related videos. Till then, goodbye. We'll be back again to the another video. Till then, keep learning, keep exploring. Thank you.